Hello guys, in today's lecture I am going to explain about electrolytic conduction from electrochemistry. So before this we need to know about conductors. What are conductors? Conductors are the substances which can conduct electricity, and as you all know, conductors are of two types. One is metallic conductor and another one is electrolytic conductor. Metallic conductors are the conductors which carry electricity by the valence electrons, the electrons. Okay, so example of metallic conductors are metals, you can say nickel, copper, iron, zinc. They are metallic conductors. And the electrolytic conductors are those conductors which conduct electricity due to the mobility of the ions. So NaCl is a conductor when it is dissolved in water, means aqueous solution when NaCl is a conductor, but NaCl solid is not a conductor. Okay, so basically in electrolytic conductors the carriers of electricity are ions. Okay, and in case of metallic conductors the carriers of electricity are electrons. Okay, these electrons will be the carriers of electricity. So before this, what are electrolytes? Electrolytes are those substances which dissociate into ions when dissolved in water. So NaCl when dissolved in water or HCl when dissolved in water, they dissociate into ions. So these dissociated ions can carry electricity, so they are conductors. Okay, so before going through electrolytic conductors, let me explain some basic about metallic conductors. Suppose this is a metal, this is a conductor, and the length of this metal is m, and its area of cross section is a. So the resistance by this conductor or metallic conductor is R. And from lower classes, from class 10th I think, we all know this relation, that resistance of this conductor is directly proportional to L upon A. And if it is converted into equality, constant of proportionality rho is kept here, and this is specific resistance or resistivity of the conductor. Okay, the same this expression will be used in electrolytic conductors also. Okay, so in electrolytic conduction, suppose this is an electrolyte solution and the two electrodes are kept here, and the distance between these two electrodes, maximum distance, that will be L, and the area of cross section of the electrodes will be A. Same relation will be used here also. This is R is equal to resistivity L upon A. Okay, so this is a conductivity cell and here L upon A, this L upon A is called cell constant of this conductivity cell. This is a constant. And another point of this resistivity is that it is the reciprocal of conductivity. And in the next slide I'll explain about conductivity. Before that, let me tell you some units. Resistance is measured in ohm. Okay, this is ohm, and conductivity, this is resistivity, is measured in ohm meter or ohm centimeter. Ohm meter is in SI unit and ohm centimeter is in CGS unit. So the units of this cell constant will be per meter or per centimeter. I think it is clear. So let me tell you again that L upon A is the cell constant of this conductivity cell. Ratio of the L and the A, this is cell constant. Okay, this is also represented by in some book by G star. Okay. Now let me explain about conductivity. Conductivity is represented by this kappa. Okay. Conductivity is nothing but it is the conductance. It is the conductance due to the ions present per unit volume of the electrolyte solution. Suppose this is the electrolyte solution. In this per unit volume, suppose there are 5 ions, for example, and due to these ions, the conductance of the solution will be kappa. Kappa is the conductance of the electrolyte solution due to the ions present per unit volume. Suppose this is the unit volume. In this unit volume, number of ions present is 5. So due to these 5 ions, the conductance will be called conductivity. And now suppose if water is added to this electrolyte solution, then its volume will be increased. Okay, volume is increased now, so the number of ions present per unit volume, same unit volume, but in this case, since the volume is large, number of ions present in this per unit volume is less. Okay, suppose we supposed number of ions in this per unit cell was how much? 5. So when the volume increases, number of ions present per unit volume will be less. Suppose this is 3. So due to these 3 ions, the conductance will be conductivity kappa 2, and due to these 5 ions, the conductivity is kappa 1. So since the number of ions is large here, the conductivity will be more, and here number of ions is less, so conductivity is less. So kappa 1 will be greater than kappa 2. So this is the question here. Can explain how the conductivity of an electrolyte solution varies on dilution. Dilution means decreasing concentration. On decreasing concentration, the answer of this question is conductivity decreases on dilution. It is because number of ions present per unit volume decreases on dilution, since the volume increases, and hence conductivity decreases. Okay, so let me go to the next slide. This is the conductivity, which is the reciprocal of resistivity. So units of conductivity will be, units of resistivity was ohm meter, so units of conductivity will be per ohm per meter or per ohm per centimeter. Per ohm is also called Simon or mho, so this will be Simon per meter or Simon per centimeter. Simon per meter is in SI units, and Simon per centimeter is in CGS unit. Okay, the next important topic for this electrolytic conduction is molar conductivity. Molar conductivity is the conductance of an electrolyte solution due to the ions, okay, due to the ions of 1 mole of the electrolyte in V volume of the solution. The volume of the solution can be any volume. It can be 1 liter, it can be half liter, it can be 10 liter also, but the amount of the electrolyte that must be present in the solution must be 1 mole. So from that 1 mole of the electrolyte, there must be some ions. Due to that ions, the conductance due to that ions will be called molar conductivity. Molar conductivity of an electrolyte solution is defined as the conductance due to the ions of 1 mole of the electrolyte in V volume of the solution. Okay, suppose if we take NaCl as the electrolyte, and if it is dissolved in water, what amount of the NaCl must be added so that we get 1 mole of the electrolyte, that is in terms of mass 58 gram. 58.5 gram is the mass of 1 mole of NaCl. So when we dissolve 58.5 gram of NaCl in any volume of water, then from that solution some ions, some Na plus ions and Cl minus ions will be there. Due to those ions, the conductivity will be molar conductivity. Okay, so next let me go to the next slide. In this slide I am giving the formula to calculate molar conductivity. Here two formulas are here. Conductivity into 1000 divided by molarity, m is molarity, and conductivity divided by 1000 into m. This formula will be used when conductivity is given in Simon per centimeter, sorry. That is when kappa is given in, when conductivity is given in CGS unit, then we must use this formula to calculate molar conductivity. Molarity will be in what, mole per liter. Okay, so by using this formula, when we calculate the value of lambda m molar conductivity, its units will come out as per ohm centimeter square per mole. Okay, I'm explaining here how this value this units comes. Okay, so another formula is this one. This must be used when conductivity is given in SI unit, that is in Simon per meter. In Simon, if the conductivity is given in Simon per meter or per ohm per meter, then we must use this formula to calculate molar conductivity. And when you calculate the units of molar conductivity will come out to be Simon meter square per mole. Okay, so here I'm explaining how these units come out. Lambda m is kappa by molarity. Kappa by molarity 1000 has no unit, so kappa is measured in per ohm per meter, and molarity is mole per liter. When we expressed liter, liter is a common unit of volume, not SI unit or not CGS unit. If we want to convert this into CGS unit or SI unit, we must change it into meter cube or centimeter cube. Suppose in this case I am just converting this liter into meter cube, so this is per liter, and therefore this will be per meter cube. Okay, so if we want to convert it into CGS unit, then liter must be written in per centimeter cube. Per liter must be written in per centimeter cube. Okay, the conversion factors or conversion constants must not give here. Okay, so after this let me go to the next slide. The next slide is question. The question is, the conductivity of a 0.2 molar HCl solution is 0.024 into 10 per minus 3 Simon per centimeter. This is given in CGS unit. Okay, this is given in CGS unit. In CGS, Simon per centimeter is CGS. Okay, so we need to use this relation to calculate molar conductivity, right? So okay, so temperature is also given. Temperature is not required. Calculate the molar conductivity of solution. So kappa is given here, molarity is given, so kappa is given in CGS unit, so we must use this formula. Kappa is here, solution, in solution molarity is 0.2. We need to calculate lambda m. So by using this formula, kappa into 1000 by molarity, kappa is substituted by 0.024 into 10 to the minus 3, and 1000 is 10 to the power 3, so this 10 to the power minus 3 and 10 to the power 3 are cancelled out, and when we divide 0.024 by 0.2, we get 0.12 Simon centimeter square per mole. Centimeter, because kappa is given in CGS unit. Okay, let me go to the next problem. This the question is, the resistance of a conductivity cell containing 0.001 molar KCl solution is left here, is 1500. Okay, 1500. Okay, so ohm at 298 Kelvin. Calculate the cell constant of the cell if the conductivity is this much at 298. So here resistance is given as 1500 ohm, conductivity is 0.0146 into 10 to the minus 3 Simon per centimeter. This is given in what? CGS unit, okay? And molarity is 10 to the power minus 3. Molarity is, this is the molarity, 0.001 molar. This will not be required in the solution, but still I'm writing here. We need to calculate L upon A, which is the cell constant, okay? So we have this relation, R is equal to resistivity into L upon A. So from here, L upon A cell constant is equal to R divided by rho, and 1 upon rho is nothing but conductivity. Conductivity is the reciprocal of resistivity. So substituting the values of resistance and conductivity, we have calculated this value. This is in terms of I forgot to write the units of cell constant here. This must be in per centimeter, okay? This must be in per centimeter. Okay, then we go to the next question. This is a very good question for examination point of view for 12 standard. Discuss the variation of conductivity and molar conductivity with concentration or dilution. So I have already explained about this first question, conductivity. In this I'm explaining about the variation of molar conductivity with decreasing concentration, or with dilution. So here lambda m is kappa by molarity. Molarity is nothing but number of moles by volume, okay? So this is equal to lambda m is equal to kappa into volume divided by n is number of moles. So lambda m upon kappa is equal to V upon n. This is just a way to know the variation, means how conductivity and the molar conductivity changes when concentration decreases, okay? So lambda m divided by kappa is equal to V upon n. So on dilution, we're going to add water. Amount of water will increase because we are adding water to decrease the concentration. So volume of the solution will increase. When volume of the solution increases, conductivity will decrease since they are inversely proportional, and molar conductivity will increase, okay? In the previous question, I have already explained why conductivity decreases on dilution. So in this case, I'm going to explain why molar conductivity increases on dilution, okay? So this is the relation when in dilution volume will increase. Since volume increases, molar conductivity increases. This is just the variation, okay? This is not the explanation, this is not the reason. So the reason here I'm discussing here, on dilution or decreasing concentration, the value of lambda m, which is molar conductivity, increases both for weak and strong electrolytes, okay? For weak and strong electrolytes, the reason for increase in the value of molar conductivity are different, okay? So here I'm explaining about electrolytes. Electrolytes are those substances which produces ions when dissolved in water, okay? NaCl is an electrolyte because when it is dissolved in water, it forms Na plus and the Cl minus ions. Similarly, ICl is also an electrolyte because it is when it is dissolved in water, it produces ions which are H plus ion and Cl minus ions, okay? Similarly, acetic acid is also an electrolyte. When dissolved in water, it produces H plus ion and acetate ion. Now in this case, electrolytes are of two types, okay? As I have already explained mentioned here. Now strong electrolyte, Se is strong electrolyte. Strong electrolytes are those electrolytes which completely dissociate into ions when dissolved in water. So NaCl will not be left because it will be converted into ions 100%. Okay, so such electrolytes NaCl and HCl or HNO3 or H2SO4 or sodium hydroxide, potassium hydroxide, strong acids and strong bases are strong electrolytes, and most of the salts are strong electrolytes. Okay, and acetic acid is a weak acid. This is a weak electrolyte because it dissociates partially into ions. Okay, so now let me explain for these two. I have written here for weak electrolytes. Okay, on dilution, on decreasing concentration, the dissociation into ions increases. Okay, the dissociation into ions increases, so we are going to get higher number of ions on dilution in case of weak electrolyte, because before adding water they dissociated partially, but after adding more water, dissociation into ions increases, means the reaction move forward and number of ions increases, so conductivity increases, hence molar conductivity also increases. But in case of strong electrolytes, examples are here. In case of strong electrolytes, this dissociation into ions does not increase here, because strong electrolytes are those electrolytes which dissociate completely into ions already. So decreasing concentration by adding water does not increase the number of ions produced. But when we add water, the volume of the solution increases. When the volume of the solution increases, the ionic mobility increases. So when the ionic mobility increases, since they will carry the electric current in electrolyte conductors or electrolyte conduction, since the ionic mobility increases, the conductivity will also increase. This is true here also. Since the volume increases, the mobility of these ions will also increase, but this factor is overweight by by the factor of increase in number of ions. In case of weak electrolytes, number of ions increases actually, because dissociation increases. In this case number of ions does not change when adding water, but when adding water, the volume of the solution increases. Since the volume of the solution increases, the ionic mobility increases. Okay, since the ionic mobility increases, the molar conductivity will also increase. So in case of strong electrolyte, the variation of lambda m, okay, lambda m and the concentration C is given by this equation, which is called Onsager equation. Lambda m is equal to lambda m naught or lambda m infinity minus a under root c. This a is a constant, solution constant, and c is the concentration, and the lambda m naught or lambda m infinity is what? Limiting molar conductivity. Okay, limiting molar conductivity is the molar conductivity of the electrolyte solution at infinite dilution, or when the concentration of the solution approaches 0. Okay, in the next video I am going to explain about this molar conductivity at infinite dilution, but for this video I am just drawing the graph for molar conductivity and the under root of c. So in this direction concentration increases, but I explained about decreasing concentration means dilution, so we need to go this direction. When the concentration decreases, molar conductivity of strong electrolyte increases, okay, linearly. Okay, so this is from this graph, this straight line is from that Onsager equation. Okay, so when we extrapolate this up to this lambda m axis, we are going to get the value of lambda m naught or lambda m infinity, because this is at infinite dilution. This is the value of lambda m at infinite dilution. Why I'm telling this? Because infinite dilution is when the concentration approaches 0. So this origin represents concentration 0. When the concentration of the electrolyte solution approaches 0, the value of lambda m naught will be equal to the value of lambda m will be equal to lambda m naught. So this can be obtained by extrapolating this straight line. Okay, now in case of weak electrolyte, the variation of lambda m and under root c is like this curve. So we cannot determine the value of lambda m naught for weak electrolytes, but there is a way to calculate lambda m naught or lambda m infinity for weak electrolytes. That is, there is a law which is called Kohlrausch's law that will be explained in the next video. Okay, so for this video let me stop here, and please like this video, share with your friends, and if you are new to the channel, please subscribe to the channel and also press the notification button so that whenever I upload a new video you get it immediately. Thank you.